Good morning. Today is June 16th. Nobody's here yet. It's 9:20. So I'm just going to go through some of the highlights that I wanted to cover today. We're up to day 13. Just a couple more topics are left, and then we'll review tomorrow for the final. We'll also do integration by parts tomorrow, which would be, like today, would be a good day to be here because it's not that hard. It's a little bit weird, but once you practice them a few times, they're fine. But I was going to do another arc length problem. So that was chapter 8, section 1 that I went over yesterday. I was going to do one together if anyone showed up, but no one is here. And I've already practiced them enough. So if someone shows up, I'll just back up the truck and do some practice problems. Otherwise, contact me if you want to work through a few together. Anytime I'm available, I'd be happy to jump into the Zoom and do that with you. Or meet with you somewhere. Coffee shop in Rapid. I don't even really know a good coffee shop in Rapid. You guys probably do though. Or an ice cream store. I do know those. I'm getting off topic, but sort of weird teaching to an empty room, but it's also sort of like when you teach fully online, you just make videos and talk to the camera and then post them and hope people watch them. So, hoping. Anyway, the topics for today were supposed to be 6.1, 6.6, 6.7, 6.8. You might think, oh my Lord, that's a lot. But this is a review of what an inverse function is that we did in college algebra. So I'm not going to reteach all that. It's in that section. I will post the PowerPoint though on the Moodle for all these sections today. So inverse functions, they just go back over a lot of things in chapter 6. The pages, if you have a hardcover book, are blue, and those are the pre-calc topics that they know that some people might not have seen, like at our school. We do cover inverse functions, but we do not cover hyperbolic functions. Anyway, 6.6 was inverse derivatives of inverse trigonometric functions. And normally in a regular situation, you'd have to memorize all these formulas. So I'll post the formula page again from reference page 5 from our book. But obviously you guys don't have to memorize all the formulas. So I'm not spending a lot of time with it, honestly. There's more fun things to do. We only have a few days left. This is your hyperbolic functions, which I honestly haven't even seen in very many pre-calculus curricula. So hyperbolic functions look like this, for example. They're so common that they got their own name, the phenomenon. So like this would be called the hyperbolic sine of x. And that one is e to the x minus e to the negative x over 2. So like you could say with any numbers, like what if x was 1? You could substitute in 1 and find what that equals. You could graph these if you have decent technology for it. I haven't tried graphing them on Desmos, but you could graph them by hand if you wanted to make a table in a pre-calc class. You might do that, you know. But the hyperbolic functions have derivatives too, and inverses. So inverse trig functions and their derivatives. Hyperbolic functions and their inverses and their derivatives. And no, I'm not going to go through how we derive all these formulas and graph them, although it would be awesome if we had the time, but we don't. So I'll show the formulas and we'll practice a few. That's pretty much it. Then the last thing I wanted to go over today was L'Hôpital's rule, which is really, really handy. So hôpital is the word for hospital actually in French, and it's spelled like that. So originally it was directly named after him. Now they have changed his name into English, which I think sounds so funny. L'Hôpital's rule, because I speak French, so I think it sounds silly. So I'll still call it L'Hôpital. But if you're like, gee, my teacher doesn't even know how to write or say the name of this rule, I do, actually. So don't be distracted by that. I didn't post assignment 7 yet. Assignment 7 is going to be a worksheet on arc length. I might just throw in a couple problems of L'Hôpital's rule too. So then that will be covered. So I won't have to put in another assignment. So we'll stop at 8 assignments. Maybe 9. We probably better have 1 assignment after tomorrow. Integration by parts is pretty substantial. So that's it. Then there will be a final exam on Monday. I haven't decided if I'll put it in WebAssign or have a paper test. Probably WebAssign, but sometimes they don't have the problems I love. Maybe I'll write my own in Moodle. That might be good for me to practice too. My own multiple choice tests where you could show your work and then enter them in Moodle. All right, that's probably what I'll do. Okay, so this I was going to do, but no one's here still. It's 9:27, so not right now. Inverse functions, let's do a quick review of what those are. This is the kind that we did in college algebra, for example. Like if y equals 3x, then, let's call it f of x. Then we worked through this in college algebra, how to find the inverse function. And I usually say the inverse function like I just did, or you could say f inverse of x. You don't say to the -1. It's not to the -1. It's not the reciprocal or anything like that. So remember how we find the inverse? It's as if you switched the x and y values. Here, I'll show you via a table first. If x was 1, 2, and 3 in this function, then y would be 3, 6, 9. So the inverse function, the new function, all that happens really is your x and y values get swapped out. No, it's not that simple, of course. Like this has to be a continuous function, a real function, continuous, defined on its whole interval, or you have to define the interval that you're going to find the inverse on. And we talked about that in college algebra because a quadratic function is continuous and defined everywhere, but it's not one-to-one and onto, meaning every x gets one y value and every y gets one x value. It doesn't have that. So we can't find the inverse of a parabola. This is just a side comment. Because, for example, this y value right here has has an X corresponding over there and over there. It has two spots. So it's not onto, which is like the opposite of being one-to-one. So it's a function, but it doesn't work for an inverse unless you limit the domain like this. If you say, oh, find the inverse of y equals x squared minus 2 on 0 to infinity. Well, then you can, for sure. Because every y gets one x value and every x gets one y value, and it works. Anyway, so I'm going off topic because this one is a straight line. It is fine. You can find the inverse because they'll say find the inverse if it exists, if you remember that. So we can do it algebraically also, and we'll end up with 1/3 x. You could look at this table and see that it would work as 1/3 x, without even doing the algebraic part. But just try to remember that part, that the y values and the x values really swapped out. So we're going to talk about these mostly. We're not going to go through cranking them out algebraically like in college algebra. But mostly we think about these as like in terms of the trigonometric functions. So let's say f of x equals cosine of x. What does f inverse of x look like? We could write it this way too. You could write it that way. Inverse cosine of x. Again, don't be thinking that it means 1 over cos x. We just were working with natural logs. So it's a little bit of shaky ground, a little bit quicksandish. And let's say we can't find the inverse on its whole domain because remember what cosine looks like. It passes the vertical line test, so it's 1-to-1. Every x gets one unique y value, right? But it's not onto because it fails the horizontal line test. Look at that. There's one spot where a horizontal line crosses the curve twice. Fail, right? So we just limit the domain. So let's say we did it on, go from 0, include 0, and we could go to 2 pi, but not include it because that would be double dipping if we included 2 pi. So we can find the f inverse there. And again, I'd really rather just think about it as in a table form because your calculator will find the values for you. Be in radians. If you see pi there, you're in radian mode. That's how you know. No, it doesn't say 360 degrees. It says 2 pi. That means radians. So in the original function, f of x and x, if we have some of our main values, let's do pi over 6, pi over 4, pi over 3, pi over 2. You know what? Why don't I just go to there? That'd be easier to look at, wouldn't it? Then I could even include that. Sweetie pie. Sweetie pie. You always could double check on a graph. Well, hey, what's that going to look like? Cosine of pi over 2 is 0. So it'll be just that part of the curve. Of course, it keeps going in normally, but if we're limiting it, it looks sort of like that in a messy way. Then the cosine of these things is 1 square root of 3 over 2, just from your old table. This was pi over 4. I lost part of it. Square root of 2 over 2, a half. and 0. So there, so that's the cosine function from 0 to pi over 2 with the highlight with our favorite values, right? So what does inverse cosine of x look like? The other way around. So when the new x and y, the new x, we just switch these around. They take turn, they swap out. When x is 1, y is 0. When x is root 3 over 2, y is pi over 6, and so on. That's all that's going on. This becomes the new domain. That used to be the range, old range. These are things we did in college algebra also. Old range becomes the new domain and vice versa. So my domain goes from 1 to 0. You wouldn't write it that way though. You write the smaller number first. So the domain goes from 0 to 1. And then we double check if you ever have to call out the domain like that. Make sure none of these pop up out of that interval. They don't. They're all less than 1. They're all positive. So we're all right there. And so that's the new domain. And the new range is the old domain. So that's the idea. I just wanted to go over briefly what's going on. You have two sets. One is mapping onto the other, and they change places. So that's what inverses are all about, honestly. Oh, I'm going to pause the recording a second, grab my graphing calculator. Go ahead and graph the two of them together on the same screen. See if you could do that. See if you could limit your domain and graph them on the same screen. See what they look like. I really have just jumped into section 6.6 with that example. So just getting ahead of myself. The inverses, I also forgot to mention, are called arc as well. So we would call this also arc cosine. So just a little hand plot would be the inverse function. I'll put in green. So let's see. 1, 0 be about here. 0.87 and 0.5. Out there. Whoops. This is rough, a little bit rough, but just to get the idea of the picture. Go over to 0, pi over 2, that's 1.57. This was 1 here, so a little bit up here. So it looks kind of like this. Just this little piece of it. If you go to graph it, it might show you a different interval to start off with. So if you do it in a device, you have to tell it what interval. Then a function and its inverse are always, that's pi over 2 over here. So I don't have it exactly symmetrical. That's why it's a little bit skewed, but a function and its inverse are always going to be symmetrical on the y equals x line, which would be right about, in this case, because I have it a little bit off kilter. So that would be the y equals x line. And we sometimes show that as a dotted line just to prove like you could fold them over each other and it would be the same on both sides if my original graph had been perfectly symmetrical. So what does all this mean for us? What do we care, right? Well, we can find derivatives of inverse trig functions. So there are a whole bunch of, not a whole bunch, but there's some formulas for inverse trig function derivatives, which I'm going to put up right now. And we had this is from your book, reference page 5. Obviously, I've posted this several times now during the this past semester and in the spring as well. So if you scroll your eyes on down to the inverse trigonometric functions, the derivative of inverse sine of x is 1 over the square root of 1 minus x squared, and on from there. So I'm not sure if the way the app I'm using right now doesn't have a highlighter on there, but you can look. And then I'm going to get to the hyperbolic functions and the derivatives of the inverse hyperbolics as well, just lightly, because there's not time to just teach that whole topic. It would be fun though. But so you can find the derivative of the inverse cosine of x, for example, the derivative of the inverse cotan of x. And then knowing those derivative formulas helps us with our integrals. If we ever recognize one of those sitting there trying to integrate, for example, 1 over 1 plus x squared, if you had that as an integration and you're like, how do I do my u-substitution for that? What am I going to do? Then you could remember, oh, that was the derivative of the inverse tan function. I could just go back and find the antiderivative of that. So they're pretty handy. I'll just barely assign very much on this, just to practice a couple of the formulas really. And then if you have your x value, then, because if we're like, find the derivative of the inverse secant function when x equals whatever, and then find the tangent line to the curve and that stuff. You could do the same techniques that we did in Calc 1 with these. So in the PowerPoint that I'll post on the Moodle, there will be some practice problems with solutions that you can go through if you want, or look online, or like I said, message me and we can meet and do some practice problems. But I'm not just going to do a whole bunch of practice problems for your viewing pleasure. Okay, the hyperbolic functions. I'll show the graph of one. You know how to do this too. But let's say we have an inverse, not the inverse yet, the hyperbolic sine of x function. That's one of the formulas, e to the x minus e to the negative x over 2. So what's it look like? That's one question. So go ahead and look or sketch it in your notes. That'll help get it into your hard drive a little bit, your brain hard drive. And what if we wanted to find the numerical value of the hyperbolic sine of 2? It could be any old thing. No, it can't be any old thing. Because, let me go through there, back it up. Back it up a minute. Going to their page of their domains. here we are. 2, of course, would have been okay, but it reminded me, let's go for the domains of these. The domains for hyperbolic sine. Excuse me. It's all real numbers. And the range is also for a hyperbolic cosine. It's also all real numbers, but the range is from 1 to infinity. And you could see that if you started substituting in whole bunches of numbers like -7, that works. That's the domain. In the domain. When you substitute that into the formula for a hyperbolic cosine, you'd get a positive number greater than or equal to 1. So the other one, where's the tangent one? Tangent has horizontal asymptotes at -1 and 1. So I'll go on with that in a minute, but let's just find the hyperbolic sine of 2. I'll pause it while you think about it. So substitute 2 in for the x values in the formula. That's all. Substitute it in there, careful with your negative signs, parentheses, and it's approximately 3.627. I'll round it. You could look at graphs of these. The inverse sine, I keep saying inverse. The hyperbolic sine function is going to have kind of this look. The hyperbolic cosine it almost looks like a parabola, but it's up here at 1. It's only never goes, the y values never dip below 1. So we can graph those on our technology as well. There's a whole bunch of, since they're connected to trigonometry, they're hyperbolic identities. There's some interesting applications, like you could describe ocean waves, the velocity of the water wave with the length L moving across a body of water with depth D. So you could have a hyperbolic function that describes ocean waves, looks like this. So they're useful. They're pretty exciting. And I wish we did more of them, really. Maybe we will someday. Huh? There you go. They satisfy some identities. We can work with the graphing of the unit circle again. All sorts of good stuff could go on. But what I really just wanted to get to was to explain that we have also inverse hyperbolic functions and derivatives. So the derivatives of the hyperbolics are, these were on that chart. And look how they sort of dovetail with our old trigonometric identities and things. That's not an accident. Be careful how you write those, just for future reference, in case you have a teacher who really is interested in where you put your powers and things like that. There's more. There's cosecant, secant, and cotan. This is what I was saying, like normally You have to memorize all these. It would do you good to memorize them if you could. But right now you could look them up or have your table right there, table of derivative formulas, and all set. Cotan is the last one. So that H in there means hyperbolic. If it's not a typo, whenever you see that, you're talking about a different function, not the usual cotan function. So I would read that negative hyperbolic cosecant squared x. So there we go. There's those values. And then there's the inverse hyperbolic functions. And let me show you what those main ones. So those were the derivatives. But just to throw in one more thing, inverse hyperbolics have formulas too. And then you can find derivatives hyperbolic of them as well. So for example, inverse hyperbolic sine of x equals the natural logarithm of x plus square root of x squared plus 1. And remember, the range of the hyperbolic sign was all real numbers. So now the domain is all real numbers for this. That's how we say the domain. X is an element of the real numbers, the set of real numbers. Inverse hyperbolic cosine of x is the natural log, almost the same. So they're not very hard formulas to remember, but I don't know. Then remember the range of the hyperbolic cosine in that picture was from 1 to infinity. So the domain of the inverse is, oh, I should just write it. Like this. X is greater than or equal to 1. Because remember, the range becomes the new domain. And then let's see, I've got room for tangent, I think. And then you can find the derivatives of these as well. No, we're not going to really be doing that, but you have them on the chart and you know how to find derivatives. You know how to use your chain rule, product, quotient rule, power rule, constant rule. We know our natural logarithm derivative rules, exponential function derivative rules, other logarithms. So we've covered quite a few derivative rules this week. 1/2 natural log of 1 plus x over 1 minus x. And then the domain is the old range of the hyperbolic tangent, which was from -1 to 1. So that's the domain of this one for x, for the new x. Oh, I don't want to have a new x. I hope I never do. Sorry, I had my camera off because I have allergies today, but you don't need to see that or hear it. Huh? Then there's the derivative function, the derivatives of these. I'm not going to write them all out, folks, but their derivatives are on that page, that page that I showed. And I will post it on our Moodle again. And so their derivatives are on page 488. And please don't ever get intimidated by what they look like, because we could handle it. Oh, hi, Trey. I just started teaching to make the recording.
Oh,
because I didn't do any examples of practicing these.
Yeah, these are fine. Okay.
And then this one, I wouldn't even need technology for at all, because I know anything to the 0 is 1. And negative 0 is silly because it's not, it doesn't matter. It's 0 or positive or negative 0. So this would be 2 over 2. So that should equal just 1. Let's do one.
Okay. I see what this 0.
Okay. Mm-hmm.
Wait.
Back on here. Okay, so backing up, what we were doing was those were the inverse hyperbolics, the derivatives. And these are the ones that you and I were just doing together. So all the 6 trig functions in hyperbolic form. And yeah, they're graphable. We could find their values. They have inverses and they have derivatives. And they have derivatives of the inverses. So those are in the formula page, and we're not going to go any further with that. But we could, just so you know, everybody's got all the background for that. We just don't have the time. So I'm going to keep going to L'Hopital's rule. And then that'll be it for today. Oh, we could do an arc length together too. That's what I was going to do if anyone showed up. But let's well, why don't we do arc length first? Because I taught that yesterday. Arc length formula. I know that I'm jumping into chapter 8, and then I'll come back to chapter 6, but arc length formula. So this is like if you have a curve and you're trying to find how long is, well, I'm not going to look at the curl, that would be different, but just what's the exact length of this piece. So like in real life, we have that going on a lot. Like in real life, we don't have that much straight lines actually. But I was going to do number 9. So the formula looks like, here's your interval x values. And it's an integral of 1 plus the derivative squared with dx out here. Or if your function is in terms of like x equals, I'm not assigning any like that, but if the function was in terms of x equals instead of y equals, then you could have this be upside down also. So it's just the derivative of your function.
Okay.
But I'm going to just do an example and a practice. Example. Let's look at y equals the square root of x to the 3rd is your curve. And find the arc length. They'll either give you between 2 points or 2 x values. I'll just do the interval of x values to start from 1 to 4. So that's not this picture. Square root of x to the 3rd is not as exciting. You could graph it, see what it looks like. That's the same as x to the, we change it to a fraction exponent. It'll make it easier. So then using this formula, I think it's fun because it looks complicated, but again, we have the skills, or they start saying like, use your technology. If you don't have an integral formula page, you can use technology a lot of the time when these get hairy, but we're going to go from first find dy dx. And sometimes it's not explicitly defined. Like sometimes you have to do implicit differentiation on these when they get more complicated. Again, we're not going to go there into the heavy complication ones, but we could. You all have the skills to do it. You all act like you're a big group, that big group of yours. So the derivative is going to be 3/2 x to the 1/2. And I'm just going to write it in terms that are more comfortable for my brain. So I need to do that first, because it's going to go in the formula right there, squared. Now I could put the endpoints of the interval here. That came from here. And let's substitute in the derivative right there. 3 root x over 2 quantity squared dx. And I usually say this too, but I just skipped it. But if you graph it and look at where you're looking at on the picture, that's always a good idea to estimate how long you expect it to be. So if you get a crazy answer, then you'd probably be able to check yourself. So it's probably close to just, I don't know. If I was just guessing this, I guess it's about 3 units. Maybe between 3 and 5, I would guess, just if I was looking at the picture of it. What it looks like is kind of boring looking, this one, but the curve is going up here. And we're looking at this part from where x equals 1 to x equals 4. So we're looking at part of the curve. So you see, you almost could approximate it with a straight line, but that wouldn't be as exact, and we're getting to the exact life. So that was y equals square root of x
To the 1/2.
Yep. So now I'm just going to work right on this page so we don't lose anything. So equals from 1 to 4 square root of 1 plus squaring this business up in here. 3 squared is 9, 2 squared is 4, square root of x squared is x. So I'm still not plugging in any values or anything, but just putting 9/4 x dx. And now we integrate using our u-substitution. So that's the next important piece, is we're going to let u be what is inside of that bracket or the radical sign. Find the derivative of that. It's just going to be 9/4. And then the reciprocal of that is what we have to multiply the front of the integral by to balance it. So that's going to be 4/9. And then we're going to have, we don't know that these yet. We didn't do those yet. So I'll fill those in a second. I'll just put little stars there. Because when we switch over to u, those change. And then we've got u, square root of u is u to the 1/2 du. So that's what we're going to integrate. I'll use this here to say, okay, when x equals this, u equals 1 plus 9/4 x. And so I can change my limits of integration when x equals 4 u equals 4 plus 9/4 times 4. 10. So this is going to be 10. And this is, and then no panicking about fractions too. Everybody has enough knowledge now to handle those bad boys. That 13/4 is too squished, but
It'll do.
okay. So now we're going to have 4/9. Add 1 to the power and divide by that. So it's u to the 3/2, divide it by 3/2, which ends up to be that. From 13/4 to 10. And anything divided by an even number, you could change that to a decimal because it'll be an exact decimal. So if anyone wanted to do that, they can. And then these, yeah. So anything divided by an even number, just get the fraction out of the way if you want to. Now these are just constant coefficients there. They can combine to get them out of the way. That's what I do when I'm doing these. So I'm going to put 8/27 in front of all the action. This is u to the 3/2 is the square root of u to the 3rd from 13/4. So what would that be? 3.25. Let's change it to a decimal. Great, I'm almost done. Then I used a calculator. So use a calculator for this last part. So we're going to take the square root of 10 to the 3rd minus the square root of 3.25 to the 3rd. I love the arc-length formula because it combines derivatives and integrals and u-substitution. And it looks really hard, but if you pay attention and take it slow, I don't think they're that hard. I think like finding the volume of a rotated solid is a lot harder, I think.
Oh,
So
yeah.
8/27 times the square root of 10 to the 3rd minus the square
Where
root
did
of
we
3.
get to 8/27?
Right here. 4 times 2 and 9 times 3. I just pulled them out of there so they wouldn't be crowding it up.
I was combining like terms first. Multiplying.
And they could stay in. It should still work out okay. It should still come out to the right answer if they stayed there.
Well, I was adding them. I don't know why.
Oh,
Like 12/27, like 8 plus 8 or whatever it is. It's like a false alarm.
and then I had just left this in exact form. Sometimes they'll say leave the answer in exact form, and then that's pretty much all they want. But I wanted a decimal form. So I'm taking 8/27 times the square root of 10 to the 3rd minus the square root of 3.25 to the 3rd. And see if you get this 7.26.
0.035. Well, no.
Well, you're close, but let me make sure mine's right too. I got 7.634, but that could be from rounding too. Yeah, it should be about 7.633705. Oh, another thing, depending on your device, I'm also kind of saying this for the recording in case anyone's watching later. It might be easy for some people to just do 10 to the 3/2 power minus 3.25 to the 3/2 power in their calculator. Just depends on what they're working with. Should still come out the same. Because because when I put the radical in there in the parentheses in my calculator, sometimes I forget to close the parentheses and stuff.
Yeah. Oh, my God. Come on, man. Time. Screen. There we go.
So we'll go ahead and start. Just set up one that's a trig function. I think we'll just set one more up because we have one more thing to cover today. Are you free all the way till 11, or do you have to go back to your internship?
It's going right now, but I'm just kind of letting them know that it's their last few days of class. So.
Okay. Well, I won't keep you very long. Don't worry.
Oops. Of course.
Okay, so here's one more with trig on it. We'll just set it up. This is number 3 in the book, section 8.1. So again, I don't get into really hairy ones of these where you would need your integral formulas and technology, just in case some people don't have their technology. So, but I'll talk about the integral formulas tomorrow in class. So anyway, what this would normally look like, the sine curve from 0 to pi is sine of pi over 2 is 1. It just looks like almost like a half circle. So that's what we're talking about, that piece of the sine curve. So we want to know how long that green piece is. And remember, pi is around a little bigger than 3. So our answer is going to be definitely more than 3, probably not more than 6. So I would just like estimate first, then set up the formula. The arc length is going to be 1 plus the derivative of sine. Almost forgot that, from 0 to pi. So that's the first part of the setup. And like I was saying before, always go like, well, what's the derivative of sine? That's cosine. So we're going to have 0 to pi square root 1 plus cosine squared x dx. And then we could start working with our integration and the u-substitution, etc., or use technology and keep going from there. So I'm just going to leave that one set up. So that's the setup. We could finish that tomorrow, or you could do it on your own, or just keep it in the back of your mind. But that would be how to set up a trig one.
This is where I get caught up sometimes, how to even set it up at first, and then especially with tricks. I don't know why I'm bad at trig. I'm better at calc than I'm at trig. That makes sense.
Well, and I don't think I give enough trig examples, so because they're weirder, so that's my fault too. So that's why I just wanted to put one out there, so
No,
you
yeah,
saw it. Yeah,
it's nice to see them because they are daunting. They really are.
Yeah. And if you have a TI, you can find a definite integral like this right away. So you can find any kind of crazy integral, even if you don't have a formula for it with a TI. So that's good to know too. So I'm not ever going to ask anybody to show all the steps for one of these, but they can if they want partial credit. Like, well, I could set it up, and then I'm stuck.
Leave it there. Okay. Oh, on the bottom. Okay.
Oh, I should set up. I'm going to set up one more that has the backwards. No, I'm not. I'm going to put the backwards way. Screw it. And we're going to go on to L'Hopital's rule and then stop. Do you need a break for a second, or are you good?
No, we're good.
Okay. So L'Hopital's rule is one of my favorites too. So I always want to make sure we talk about this. So this is 6-8. They call it Hospital's rule in our book. Oops. Because hospital is English for L'Hopital, but his name was really this, so I still call it that. So that's what they called it when I learned it. And so this is a wonderful invention. So if you can't find, if your limit comes out to be, back to limits, to finish strong with limits, if your limit comes out to be indeterminate like that, or infinity over infinity, so that's called indeterminate. Indeterminate. Those are called indeterminate, not undefined. That's different. So if your limit comes out like that, and you're like, well, damn it. And you usually, before we would just write it does not exist or something, or you can't find it. But now we can use this formula, which is just great. So you use this. So first you try, I'll show, like we try and do a limit normally. So we'll just review a couple limits from long ago. But the limit of a rational function is going to be the limit of the derivative of the top. So it's not the quotient rule. You just do the straight up derivative of the top, derivative of the bottom, and then substitute. And if you get an actual number that's not indeterminate, that's the answer. Sometimes that doesn't work either. So you go one more step, or I guess you could go more, but you won't have to go more than one extra step. The second derivative over the second derivative of the bottom. If you could substitute a value into that, that'll work too. So let me just explain what am I talking about. Let me do one that doesn't have lns or anything in there for starters. What ones was I doing before? Oh, this one, I love this. This is a good starter. So the limit as x approaches 1 of x to the third minus 2x squared plus 1. So this is kind of an old school kind of one that we did in Calc 1. And the first step is always, could I just substitute in 1 and see what I get? That would be the best. Review the steps for limits. So step 1 is substitute. So if I substitute, I'll get 1 cubed 2 times 1, 1 minus 1. So I'll get 0 over 0. That is my problem. It's indeterminate. Looks like I wrote IE. So then my next step would be, well, can I factor or do any of those algebra tricks and simplify, cancel something and substitute? Can I do those algebra tricks like divide the top and bottom by the numerator and things like that? We also did, this is a little bit not as approved, but you can also look at a graph or table. In fact, you can verify this because this is what's happening to y as x gets closer to 1 on both sides. As x moves in close to 1, whoops, what is y getting close to? That's just the only thing that we're trying to find out, but without looking at it. All right, so it's indeterminate. There, I tried, I'll tell you already, I tried to factor it and that didn't work. That direct substitution didn't work. I don't see an algebra trick that I could do or arithmetic. So we'll go on and take the first derivative of the top and bottom. So derivative of the top and the derivative of the bottom. And don't double check that you see where I got those numbers from. You're okay with that?
Oh, yeah, yep. Just 2x, 3x, 3x,
And then try to substitute again.
You don't have to do the quotient rule right here or anything because you're not.
No, it's crazy.
whole-
Yeah. No, it's
Sweet.
just a little trick that L'Hopital discovered. And there's extensive proofs of it too in chapter 6 at the end, but I'm not going through the proofs even. You can if you want. But I'll post the PowerPoints for anybody who's into it. So substitute that 1 in there again. So 3 times 1 squared, 4 times 1, 3 times 1 squared again. And hooray, we got an actual real number, definitely not indeterminate. That's the answer. So remember about limits too, at x equals 1, the whole function is undefined. So if we look at the original graph, there will be an asymptote there. But on each side of x equals 1, the y value is approaching -1/3. And so that's what we found out. That one was number 11 on page 500.
So with limits, is it kind of an element of shoot, like you doing it over till you get it right, trial and error.
Yeah, exactly. Because sometimes you have to go more than one time through. I was going to show one like that too. Oh yeah, here we go. Well, we have some, these ones will just, yeah, trial and error like that, and all these different techniques that could work. That might be why people really don't like the limits, because it's one of those that has kind of some gray area, huh?
Yep.
Like not just one direct way. Yeah.
I was just gonna say that. I think that's why I like derivatives and not limits, because limits is almost like more scientific, where derivatives are still pretty mathy.
Yeah, I agree. The limit is a little more abstract. Very abstract. So let's look at,
issues.
we're going to do two that have exponentials and logarithms that we worked on this week, just to review them. So remember that the derivative of an e function is just itself. We just have to remember that from earlier. Okay, so first of all, if I put in e to the infinity over infinity squared, that's infinity over infinity, which isn't even a number. So that's definitely indeterminate. Like sometimes for limits, we do get the answer of plain old infinity, but we can't have infinity over infinity. That's not allowed. So I can't do it. So that was direct substitution. Always try that first in case someone's trying to trick you. Just try to plug that in and see if it's going to work. So we can't say that equals 1 because those aren't real numbers. So we can't say that. Anyway, so now we're going to find the derivative of the top over the derivative of the bottom and see if that'll work. So derivative of the top is itself. Derivative of the bottom is 2x. So that's the first derivative of each. That's what that was. But if I plug in infinity there, I'll still have infinity over infinity. So no, it's still not going to work. So in this one, we go one more step. Find the second derivative. And you could keep going forever, actually. It says, so the second derivative is e to the x still over 2. And then direct substitute. And you'll get e to the infinity over 2, which is infinity. Ta-da, ta-da-da. So that's the answer.
You said infinity over infinity is not a thing, right?
Right, it's not a thing. But plain old infinity is still not a real number, but it's an answer for limits. We're allowed to answer that. Because like the infinity, there's different sizes. So one of them is bigger than the other. If we're looking at infinity over infinity, they're not equal for sure. We don't know for sure they're equal because they're not actual numbers. It's just an idea of bigness. So all that's saying is that this function, as x gets huge, y gets huge as well. So as x gets huge, y gets huge too. And just looking at a graph, we would know that. You would know that. You'd be like, oh, obviously it's going to be infinity. But if we wanted to prove it algebraically, then we use L'Hopital's rule. Oh, I had one more example and I flipped my page around. And this they use to talk about luminescence sensed by an eyeball. There's other kinds of really cool like physics problems that they use L'Hopital's rule with these kind of limits. So it's kind of handy. But anyway, one more example. And I'll promise I'll be done. Wanted to do one that had a natural log in it because we did that this week too. So this is the last one. Find the limit as x approaches 1 of the natural log of x over x minus 1. So again, we go through our steps. The first step is always direct substitution. So if I substituted this, the natural log of 1 over 1 minus 1, natural log of 1 means e to the what power equals 1. Natural log is a log base e. So e to the 0 equals 1. 1 minus 1 is 0. So there's another indeterminate. So it's no good. And we can't say that equals 0. And we also can't say it equals 1. Although people always argue with me, like, why? Why can't we say that equals 1? Because 0 divided by anything is 0.
Yeah.
We can't say it's 0 either.
I know, it's kind of a weird one. Trips up the
Very weird.
calculator.
Yes. So now let's do the limit of the first derivative of the top and the first derivative of the bottom. Whoops. And I'm glad you asked that about the quotient rule, because sometimes if people are tired, I started doing the quotient rule when I was practicing these, because it just like, it's my go-to.
Just sounds right. It looks right.
Yeah. So note is that the derivative of the natural log of x is 1 over x. X has to be greater than or equal to 1. So x has to be, x is positive, but we're good because we're talking about the limit as x approaches 1, not 0. 0 wouldn't have worked for this. Anyway, the derivative of the top is 1 over x. The derivative of the bottom is 1. Simplify. Substitute directly. Equals 1. Hooray! So that would should be visible on a graph as well. If we looked at it, again, we're just saying as x gets really close to 1, y also gets really close to 1. Even though it's undefined at 1. Undefined at x equals 1, because that would make the bottom equal 0. So the graph would have either, I didn't look at the graph, definitely have a hole or an asymptote right there. But we could still find the limit. It's fantastic. So that's L'Hopital's rule, or hospital's rule, however you want to say it.
I thought it was hospitals too, honestly.
And I didn't post assignment 7 is going to be the last paper assignment. So it's going to have a couple practice problems of this rule, and maybe one arc length problem. Maybe one like find one or two, find the value of hyperbolic cosine of 5 or something like that. That's
Okay.
it. So it won't be very extensive. We'll just touch on these topics.
Okay, sweet. Yeah, I need to work with them a little bit. And then, yeah, I'll send this to you. Or if there's a spot on Moodle,
right,
I can just put it on Moodle.
There should be a spot on Moodle, but really whatever's easier. You could Google share, email, post it, text it. I don't care. We'll find it. All right, well, I'll let you go. Thanks for showing up, Trey. I appreciate it.
Yeah, no, thank you. I needed, so appreciate it.